Hello, welcome to my next topic in the lecture series on quantum mechanics. And let me introduce me once again. I am Professor N.K. Pandey from Department of Physics, University of Lucknow. And in the lecture today, I am going to discuss on the Broglie waves. The Broglie waves is a very important topic in quantum mechanics, and that you can say establishes a link between the classical mechanics and the quantum mechanics, and you can say that it is the linking thread between the two mechanics, the classical and the quantum. So let us first of all consider three effects: the photoelectric effect, the quantum effect, the Compton effect, and the Davison and Zermer experiment. Now, in the photoelectric effect, what I have already discussed about this topic in earlier lecture, that the electromagnetic radiation in ultraviolet range is made to irradiate on a metallic surface, and metallic surface ejects electrons. Now, this photoelectric effect could not be explained on the basis of electromagnetic wave theory, and the help of quantum theory was taken to explain the photoelectric effect. Starting from Max Planck, who proposed that from any body the radiation came out in the form of small bundles or packets of energy called quanta, and they propagated in a space, the radiation propagated in a space as continuous waves. Einstein proposed that these packets of the emission was in the form of packets or bundles of energy, and they propagated as packets or bundles of energy as well. So because these electromagnetic waves are propagating as quanta or bundles of energy, they are carrying momentum, and because they are carrying momentum, they behave like particles and make collision with other particles like two particle collision. And therefore the photoelectric effect could be explained on the basis of quantum theory. And if you remember Einstein's equation, h nu is equal to h nu naught plus T maximum. Here nu is the frequency of the radiation falling on the metallic surface. Nu naught is the threshold frequency, and T maximum is the maximum kinetic energy carried by the energetic electrons. Now let us go for the Compton effect. Here, an incident photon, the X-ray photon, is being scattered by target electrons, and the scattered photon contains two wavelengths: one the original wavelength, and the change, that is the higher wavelength. Now, the presence of original wavelength in the scattered photon could be explained on the basis of electromagnetic theory, but the presence of both the original wavelength as well as the higher wavelength could not be explained on the basis of electromagnetic theory. They could be explained only on the basis of quantum theory. And if you remember this particular formula that I have already discussed in one of my lectures on Compton scattering, then the photoelectric effect and the Compton effect both established that the waves, the electromagnetic waves, the waves could behave like particles and make collision with other particles like particle-particle collision. Now let us come for the third experiment, that is the Davison and Zermer experiment. Here, the energetic electrons are made to fall on a nickel target in which the crystal planes are regularly arranged. Now, in this Bragg reflection, classically, we should be getting the uniform distribution of electrons in the scattered beam. However, in the scattered beam, what we get is maxima and minima. This maxima and minima is the phenomenon exhibited by waves and not by the particles. And therefore, it could be concluded over here from the experimental result that electrons were behaving like waves here. Now let us sum up. This is n lambda is equal to 2a sine theta. That is the Bragg formula that was used to explain the Davison and Zermer experiment. Now let us sum it up. Photoelectric effect and Compton effect, they established waves could behave like particles and could make collision with other particles like billiard ball collision. Davison and Zermer experiment established moving particles like electrons could behave like waves. Now, the forward portion of my lecture will cover if moving particles like electrons could behave like waves, then there must be associated a wave with the moving particles, and the wave that is associated with the moving particle, what kind of these waves are? What kind of wave function is there with the wave? How the wave could be represented? How we can write it mathematically, and many such problems that we are going to see in the subsequent part of my lecture. Now, first of all, the energy of a photon is given by E is equal to h nu, that is hc by lambda. The energy is also given by the formula E is equal to a square root m naught square c power 4 plus p square c square. Here m naught is the rest mass and p is the momentum carried by the particle. Now, a photon doesn't have the rest mass, and therefore m naught is equal to 0, and so E is equal to pc. That implies if we equate the above 2 points, that is E is equal to hc by lambda and E is equal to pc, then we get, this implies that we are getting lambda is equal to h by p. Now, this expression is combining two properties, lambda, the property of a wave, and p, momentum, the property of a particle. Now, let us consider the wave function associated with the Broglie wave or the matter wave associated with a particle. The wave function here we call psi. So the wave function psi associated with the Broglie wave. Now, question is, now first of all, let us see that this wave function psi is complex. So psi is equal to a plus imaginary ib, psi star, that is a complex conjugate, a minus ib, mod psi square is equal to a square plus b square. Now, question is, what kind of this wave function psi is all about? Let us remember a plane progressive associated, a plane progressive wave y is equal to a sine omega t minus kx, and this was a plane progressive wave moving in the positive x direction, and y was the displacement either perpendicular to the direction of propagation in transverse wave or in the direction of propagation in longitudinal wave. So there, y represented the wave function of that plane progressive wave. Now, much in the same way, p is equal to p naught sine omega t minus kx, that is a pressure wave. Now, the compressions and rarefactions in a pressure wave. So here, small p represents the wave function that we call it over here psi. Much in the same way, in an electromagnetic wave, E is equal to E naught sine omega t minus kx, or H is equal to H naught sine omega t minus kx. Here, E and H, that is the electric and magnetic vectors oscillating perpendicular to the direction of propagation of the electromagnetic wave, represents the wave function associated with the electromagnetic wave. So similarly, psi is a wave function associated with the matter wave that we are going to consider. Now, how do we define psi? Psi represents the probability of locating a particle at any point in a space x, y, z at the instant of time t. Now here, because psi represents a probability, but psi could be negative as well as psi could be complex, but probability cannot be negative or complex. Therefore, we do not take psi as representing the probability or the probability density. We say that the probability density mod psi square represents the probability of locating the particle at any point x, y, z in a space at the instant of time t. So mod psi square is the probability density. Even if psi is negative, mod psi square is positive. Even if psi is complex, mod psi square is positive, and mod psi square is psi star psi. Now, what is the speed of the Broglie waves? But a natural common sense question will be there. What should be the speed of the Broglie waves? And the common sense will answer that since the wave is associated with the moving particle, naturally the speed of the Broglie waves should be equal to the speed of the particle. But is it the same that we get mathematically? Now here, let us go with the quotation of the following formula. Lambda is equal to h by mv. We have just not seen lambda is equal to h by p, where p was the momentum. So if m is the mass of the particle and v is the velocity of the particle, then lambda is equal to h upon mv. E is equal to h nu, and E is also mc square. Therefore, nu is equal to mc square by h, and therefore w, the speed, will be given by nu lambda from the above, is equal to c square by v. Now, c square by v, that is the speed greater than the speed of light in vacuum, or even the body, moving body. So, according to this particular mathematical expression, the Broglie wave has a speed greater than the speed of light in vacuum, or the moving body also, naturally. So, question is it okay? And we will try to answer it subsequently. First of all, let us see how we should be representing a wave associated with a moving particle. Now, can the following equation of a plane progressive wave, that is y is equal to a sine omega t minus kx, represent the Broglie wave associated with a moving particle? Now, if we try to show y is equal to a sine omega t minus kx graphically, it is like this. Now, this expression y is equal to a sine omega t minus kx represents a sinusoidal wave extending from minus infinity to plus infinity. Naturally, if a wave is associated with a moving particle, since particle is a localized body, therefore the wave associated with the particle must also be finite in extent. It cannot stretch to infinity, because the particle cannot be spreading itself to minus infinity to plus infinity. So naturally, a sinusoidal wave like y is equal to a sine omega t minus kx, which is represented graphically here, cannot represent a wave associated with a moving particle. It cannot represent a matter wave or the Broglie wave. So, if we try to have a picture of a wave packet, then it should be a small packet or a short burst of energy, as Planck and Einstein called it, or envelope of localized wave action that travels as a unit. And we will see how it is. How is a wave packet synthesized? Then it can be synthesized an infinite set of component sinusoidal waves of different wave numbers with phases such that they interfere constructively over a small region of space and destructively elsewhere, resulting in the variation of amplitude that defines the group shape. Now, let us see. That means how to construct a wave group. An infinite series of such waves, each one differing from each other in wave number only slightly and in frequency only slightly, on superposition will give rise to what we call a small wave packet. Now, each component wave function and hence the wave packet are solutions of the Schrodinger equation. Now here, let us consider one such wave function psi1 is equal to a cos omega t minus kx, and this will look like this. Similarly, let us consider another wave function differing from the other one, earlier one, by d omega and dk, and the wave function will look like this. And let us consider the resultant of the two, psi is equal to psi1 plus psi2 is equal to this much by the superposition principle, and it will look like this. If you remember, this looks like the phenomenon of beats in the sound waves, where two tuning forks of having slightly different frequencies from each other, when they are plucked, they give a similar pattern like the one we are seeing in psi is equal to psi1 plus psi2. Now here you can see that what we are interested in as wave group is this much extent, and this is the envelope of this wave group. Now this frequency is the average of the two frequencies of psi1 and psi2, and this envelope has a frequency which is d omega by 2, and its wave number is dk by 2. Now you can see the resultant of the superposition of two such waves, psi1 and psi2, is given by this, and this much is the wave group. The envelope is the wave group. Now here, two things we have to distinguish. One is the phase or wave velocity, which is given by omega by k, here omega upon k. And the other is the group velocity, that is d omega by dk. Nothing physical moves with phase or group velocity, and the energy moves with, nothing physical moves with phase or wave velocity, and the energy moves with the group velocity d omega by dk. Now, here one more point. If we have the superposition of only two waves, as shown earlier, psi1 and psi2, then we will have large number of such wave groups. It is only when there are infinite number of such waves, each one differing from each other in omega by d omega and in k by dk, then on superposition we get a single wave group representing the wave associated with a moving particle. Now, let us go back to the same formula, that is W is equal to C square by V. That is the that what we got. So omega is equal to twice pi nu, twice pi mc square by h. So twice pi m naught, it should be m naught c square by h, square root 1 minus v square by c square, because for relativistic cases m is equal to m naught by under root 1 minus v square by c square. K is equal to twice pi lambda, twice pi m v by h, and here it is m naught written, twice pi m naught by under root 1 minus v square by c square. In the numerator we have v, in the denominator we have h. Now then W, that is the phase or the wave speed, that is W is equal to omega by k. If you divide the two, you will get c square by v. And if you want group velocity, then u is equal to d omega by dk, and d omega by dk could be written as d omega by dv by dk by dv. And if you make calculation for this u from omega and k, then you will land up getting v as expected. So group velocity is same as the speed of the moving particle. Now let us consider one more thing. Since we have associated a wave with a moving particle, particle is a localized entity, but the moment we associate a wave, the Broglie wave or matter wave with the moving particle, we introduce an inherent uncertainty in the location of the particle. And that is, if we have a broad wave packet associated with the particle, then the location of the particle becomes so much uncertain. But the wavelength can be easily determined. But to the contrary, if we have a narrow wave packet, then determination of the wavelength is difficult, but location of the particle is easy to ascertain. So this uncertainty comes up because of the wave associated with the particle, and this uncertainty principle I have separately dealt in a lecture that is already on the YouTube. The moving wave packet or the Broglie wave. Let us visualize this. It is something like this. That is, a wave packet is moving like this, and we have over here, you can see the whole wave packet moving together. This much is the wave packet that is moving together. As you can see, there's sketch, a small video, and that explains how a moving packet looks like, or the Broglie wave looks like. Propagation of a wave packet. Now, what are the properties of the wave function psi we have discussed? Now, we have number one, the integration of mod psi square d square is equal to 1. That is the total probability of locating the particle from minus infinity to plus infinity cannot exceed 1. Psi contains all the information about the particle. That means once we have solved a problem of a particle, we have solved the Schrodinger equation, we have got psi. Then psi will contain all the information about the particle, its speed, its momentum, the wave associated with the particle, the frequency. Every such information is contained in the wave function itself. Now this psi must be a solution of the Schrodinger wave equation. It must be continuous function of x, and the slope of the function in x, that is del psi del x, must be continuous. And if we try to enumerate it, it is something like this. You can see from here, Psi contains all the information about the particles. Psi summed over all space must be 1, must be a solution of the Schrodinger equation, must be continuous function of x. The slope of the function del psi del x must be continuous. Now, while solving a problem, these constraints are applied to the boundary condition on the solution, and in the process we get energy eigenvalues that we will see later while dealing with the Schrodinger equation, etc. Now, mathematical expression of a wave associated with a free particle. Now, mind it, a plane progressive wave from minus infinity to plus infinity has a resemblance to a particle which is completely free to go anywhere. It is not bound by any force, and therefore there is no potential energy associated with the free particle. It has only kinetic energy. So the both have got some resemblance, and therefore we can take the clue for establishing the mathematical expression for a free particle from y is equal to a sine omega t minus kx. Now y is equal to a sine omega t minus kx or y is equal to a cos omega t minus kx as the real and imaginary expressions of the exponential function that we can say psi is equal to a exponential minus I omega t minus x by v. Same as this one. Its real and component parts could be written as cosine and sine functions like cos omega t minus kx, sine omega t minus kx. So this is the expression we start with. But naturally, because we are talking about a free particle, then it must be containing the energy of the free particle, the momentum carried by the free particle, right? And therefore, we proceed with this one. Now, A is the amplitude we have considered. Now, psi is equal to A exponential minus twice pi, omega is equal to, I have broken, and omega, and this is psi is equal to A exponential minus twice pi I, Vt minus x by lambda. So, we have E is equal to h nu is equal to twice pi h cross nu because multiplying by twice pi and dividing by twice pi. So lambda is equal to h by phi as we have seen earlier. Multiplying and dividing by 2 pi gives twice pi h cross by p. So in the above expression of psi, if we put the value of, let us say, lambda from here and nu of also, then we get psi is equal to a exponential minus I by h cross et minus px. Mind it? This is a mathematical expression of the wave associated with a free particle because it is having E as energy of the free particle and P as the momentum of the free particle. So this is the mathematical expression of the wave associated with the free particle. Psi is equal to A exponential minus I by h cross et minus px. Thank you very much for your kind attention.